In the previous video, we introduced the structure of the compute unit, and we summarized the SIMD unit is one of the most important internal components of a compute unit. It is where the computing power of AMD GPUs come from. So in this video, we're going to talk about the SIMD unit structure and how the instruction issuer works together with the SIMD unit. So for each compute unit, there are 4 wavefront pools, and there are 4 SIMD units. It's not a coincidence. They're actually hardwired together. For each wavefront pool, there is a corresponding SIMD unit. The wavefront inside the wavefront pool can only be executed in their corresponding SIMD unit. The instruction issuer will take 4 cycles to launch instruction to the SIMD unit. In cycle 1, it launches from wavefront pool 1 to SIMD 1, and in cycle 2, it launches from wavefront pool 2 to SIMD 2, and so on. So let's look at the internal structure of a SIMD unit. In each SIMD unit, we have 16 lanes. You can consider these lanes as ALU unit. Each lane can process 1 operation or 1 instruction per cycle. And these lanes are only for single precision computing. For half precision and double precision computing, we have some other ALUs. And there is typically a ratio between half precision computing and single precision computing capability. In older GPUs, it's 1:1, so 16 lanes for half precision and 60 lanes for single precision. In newer GPUs, it's 1:2 ratio. That means for 16 lanes of single precision, there are 32 lanes for half precision. Moreover, we also have double precision calculation, and the ratio between double precision computing capability and the single precision computing capability varies from GPU to GPU. So for some gaming GPU, there may be no double precision computing capabilities. And for some high-end gaming GPU, the ratio may be 1:8. So that means there are 2 double precision lanes per SIMD unit. And for high-end compute-oriented and professional GPUs, it's typically a 1:1 or 1:2 ratio. That means there may be 16 lanes for double precision computing. For most of the time, we consider single precision computing capability. So there are 16 lanes, and each SIMD unit can handle 16 operation or 16 thread level instructions in each cycle. So remember, 1 wavefront equals to 64 threads, and 1 lane can process 1 thread level instruction per cycle. So that means the SIMD unit needs to take 4 cycles for each wavefront level instruction. And this 4 cycle is not a coincidence to the number of SIMD units in each compute unit. It is carefully designed. So let's see how it works. In cycle 1, we issue 1 instruction to SIMD 1. In cycle 2, we issue another instruction to SIMD 2. Also at cycle 2, let's look at SIMD 1 unit. We're executing the instruction lane 0 to lane 15. In cycle 3, we're launching another instruction to SIMD 3, but look at SIMD 1 again, we're executing lane 16 to lane 31. So as we keep going, another instruction is issued to SIMD 4, and this time in SIMD 1, we're executing lane 32 to lane 47. Finally, in cycle 5, we issue another instruction to SIMD 1, that's the issue stage. And in SIMD 1, we're finishing the whole instruction, the previous instruction that is from lane 48 to lane 63. In starting from cycle 6, the SIMD 1 can start to execute the next instruction. Since we need 4 cycles to execute each wavefront level instruction, and we have 4 SIMD units, and the instruction issuing is a round-robin process. So we actually have a perfect matching of the speed that the SIMD units can run, and the instruction issuer can issue instructions. So it's a perfect balance. It can reach the highest computation throughput. Understanding the power of SIMD unit, we can start to do some calculation. Let's calculate the theoretical computing power of a GPU. Let's use R9 Nano as an example because it is very easy to compute. There are 16 lanes per SIMD unit. There are 4 SIMD units per compute unit. There are 64 compute units per GPU. We can simply multiply these three numbers together. We get 4096 instructions per cycle per GPU. R9 Nano works perfectly at 1 GHz, and that's why we want to use R9 Nano GPU. It's super easy to compute. That means we can calculate 4.096 trillion instructions per second per GPU. We also need to consider one special case, that is the MAD, the multiply and addition or multiply accumulation instructions. That's considered as a multiplication operation and a summation operation. Let's consider two operations, and these two operations can be completed in one cycle. That goes to 8.192 teraflops. Tflops stands for tera floating point operation per second. So that's the theoretical computing power of a GPU. Although it is very hard to reach this level, it is typically, if you want to compare the capability of a GPU, this is probably the single most useful number to compare. There are two confusing concepts that you may raise at this moment. We will talk about 4096 instructions per cycle in the previous slides. That comes from 16 lanes for SIMD unit and 64 compute units. We have also talked about this number, 163,840 threads executing at the same time. That comes from 64 threads per wavefront, 10 wavefront slots, 4 wavefront pools, and 64 compute unit. So how do we understand this difference? How many threads can be executed at the same time? Is it 4,000 instructions, 4,000 threads, or is this 163,000 threads are being executed at the same time? They're both correct, it's just the way we understand it. We can say it in this way. Out of the 163,000 threads waiting there to be executed, only 4,096 can be executed in the SIMD unit in each cycle. Since the SIMD unit is the unit that provides the computational power, we only consider SIMD here. This actually gives another understanding about thread level parallelism. Remember, in the first unit, we were talking about thread level parallelism. We were talking about the difference between the CPU and the GPU. While there are some threads are doing real work, doing the work for SIMD unit, there are some threads are doing the overhead work. For example, loading data from memory, calculating some addresses using scalar instructions. The overall goal is to fully utilize the SIMD unit. But to fully utilize the SIMD unit, we need to have sufficient data waiting there to be executed. So some threads may be working on fetching data to the compute unit, while other threads can start to work for SIMD unit. And the number of 40 wavefront that can be executed in one compute unit is generally a good match for the computational capability. Of course, this differs from workload to workload. Some workloads are more compute intensive, some workload may be more memory intensive. For the most commonly executed workload, such as matrix multiplication, we want to have a full utilization of the memory bandwidth and the SIMD computational power at the same time. Moreover, we need to talk more about instructions. As you may hear, I may sometimes talk about thread level instructions and work level instructions. How many instructions we can execute at the same time? So for one issuer, we can issue one SIMD instruction per cycle. Now for each SIMD, we have 64 instructions per CU per cycle being executed. So how to understand the difference is one is wavefront level instruction and one is thread level instruction. The issuer issues at wavefront level, so that number 1 is wavefront level instruction. Then number 64 is thread level instruction. One wavefront level instruction is equivalent to 64 thread level instruction. However, we still need to consider predicated instructions. So when our execution mask is some extreme value, for example, if our execution mask is 1, out of these 64 thread level instructions, only one is predicated and will take effect for instruction execution. So in this case, one wavefront level instruction is equivalent to one predicated thread level instruction. Remember, it still takes 4 cycles for the SIMD unit if it's predicated in this way. you're actually taking 4 cycles to execute only one instruction. That is actually a waste of the computational power of SIMD units. That's why we want to avoid thread divergence. We want to keep the execution mask as full as possible. Finally, another concept that keeps being asked and people get confused is the context switching in GPU. So this is a complex question. We should not really answer what's the overhead of context switching in GPUs. There are different levels of context switching. So kernel level and block level switching, assuming let's say one kernel is executing there or one block is executing there, we want to swap out that block and bring in another block in. The quick answer is it's typically not supported by GPUs. There are some modern GPUs, there are some theoretical GPUs that only exist in research papers. Yes, it's being discussed, but it's not generally supported by currently available commercial GPUs. Then we talk about thread level and wavefront level switching. So considering the instruction issuer is issuing instructions from different wavefront and different threads, basically we can say it's cluster-free. There's no latency for context switching for GPUs. You can understand GPU as a super hyper-threading machine. There are a huge number of threads waiting there to be executed. Typically in hyper-threading CPUs, you can only see 2 threads waiting in one core to be executed. But for each GPU, hundreds of thousands of threads waiting there to be executed. Until now, we have a full understanding of the computational side of the GPU architecture. In the next video, we're going to go through the memory hierarchy of a GPU.